Well, this is a very nice experiment. Atwood's machine is a great demonstration of Newton's second law. As I mentioned in the write-up, Newton sort of verified his second law by calculating the period of the moon going around the Earth, and Atwood wanted something to, with both hands in front of him, he could experiment with to also verify that the net sum of the forces, the vector sum of the forces, equals the total mass of the system times its acceleration. So that's what we're going to do. We have a machine that's just about as simple as you can have. We have two smart pulleys, and we have these weight holders hanging over with weights on them. This is, we're going to call this M1 and M2. M1 is going to be greater than M2, so the system's going to rotate this way. Again, I explained this in the write-up. We want to use the plus direction as the direction of motion of each mass, which means that this mass is going down and this mass is going up, and so this is the plus direction for mass 1, and this is the plus direction for mass 2. That keeps all of our signs in synchronization with each other in our calculations. So these two pulleys are smart pulleys, and they have a very low friction axis, axle bearings, and they have a mass of 5.5 grams. We can't take them apart to double check that, but I'm sure they're quite accurate. The company that made these is a pretty good company. So they total 11 grams, and as I mentioned in the write-up, and you're going to talk about this later in class, these objects are not moving in a linear direction, they're rotating. That's a lot more complicated, and in that case you use what's called the moment of inertia rather than the inertial mass. Really, that's the full name of these masses. If you do all those calculations, and because these are so light compared to the masses hanging down here, it turns out that we're just going to be able to ignore those complications and just use the mass of the pulleys in the experiment as part of the total mass. So total mass of the system is M1 plus M2 plus 2 times the mass of the pulleys. That's what's accelerated. The string, which you can check mass as you will in the procedure, is a couple tenths of a gram. It really doesn't make that much difference, but this is a pretty accurate experiment. So when you weigh the total mass of everything, masses on this side and masses on that side, you might as well weigh the string with it and add 11 grams to the total to get the two pulley mass values. So that should be the total mass of the system, total system mass. Again, ignoring the slight complications from the rotational business. So, Newton's second law, as you know, is the vector sum of the forces equals mass times acceleration. It's a vector relationship, but the motion in this case, the pulleys don't go anywhere, they just rotate. But the motion in this case is simply vertical, so we have a one-dimensional system, and that means we don't have to use these vectors. So that's nice. And so this becomes simply F equals ma without the vectors, where m is the total mass of the system, and you can probably figure this out. The force, the net force, is simply the weight difference times, don't forget the acceleration of gravity, turn this mass into a gravitational force. This is the weight difference, and so this is the left side of this expression. Now, the only little catch here, which is a pretty minor catch, is that there's friction in these pulleys. And of course, we use the symbol little f for friction. And so the sum of the forces is the weight difference between the two pans, and minus the frictional force. Frictional forces always act against you. So we have M1 minus M2 G minus the frictional force, which is always acting against us, is equal to the total mass times the acceleration. The total mass is, again, this value here. Okay, so if I move the frictional force over the other side, I have M1 minus M2 times G equals mass total, that's the mass on the left plus the mass on the right, plus 2 the pulley masses times the acceleration minus the frictional force. Okay, this is in the form of a straight line, such as y equals mx plus b. So this is the accelerating force. X, your graph is going to be force versus acceleration. And you're going to measure the accelerations in 5 different instances and get them to make you a graph, hopefully linear graph, which you can use the graphical analysis to draw a nice straight line through. And because there is some friction, this little distance here is the y-intercept, which is minus the frictional force. So you can get the frictional force from your graph, and of course, as you know, friction is fun. And so you can, if you know the frictional force and you know the normal force, and the normal force, of course, is simply the weight of everything that's pushing down or pulling down on these pulley axes, causing the friction at the bearings, you can find the coefficient of friction, which is going to be really, really small, like 0.0 or maybe even 0.00 something. And it's just a number, it doesn't have any units. So that's our experiment. And it really is a beautiful experiment to verify Newton's second law, because we have only one independent variable. That's the difference in the weight you put on this, and the corresponding dependent variable, which is how much acceleration occurs when you have that weight difference. So everything else, we've kind of included friction in the story, but the friction is obtained simply by looking at y-intercept on your graph and literally subtracting it out from the picture. So this is a really, really good verification of the net sum of the force on a system equals its mass times acceleration. So let's take a look at the apparatus and just see how it goes. Thank you. Okay, this is the Atwood's apparatus, and as I said, it's got 2 pulleys, and they have a mass of about 5.5 grams, pretty close to that. And they're called smart pulleys because they're smarter than the average pulley. And they have 10 spokes and a circumference of 15 centimeters, which means as they rotate from one spoke to the next spoke, they rotate 1.5 centimeters. And over on this side we have a Photogate, which shines an infrared beam through these spokes, and every time a spoke is broken by the beam, it has traveled 1.5 centimeters. And the program that's associated with the smart pulley in the computer understands that, so it then can calculate the position and from that the velocity and acceleration of this rotating pulley wheel as it moves. So we're going to use, as we did for our free fall experiment, a velocity versus time graph, velocity vertical time horizontal, to get the slope of that graph, which of course is delta v over delta t, which is acceleration. So you're going to be measuring, again, more than once, 3 or 4 times, the acceleration due to the different mass differences, and relate that to the mass difference times g, that is the accelerating force. That's Newton's law. We talked about that earlier. So this is a pretty slick apparatus, and I've got sitting over on the pan, double pan balance over there, which I double checked for being 0 at 0 with nothing on it. And I have sitting on this balance everything that's going to move except the pulleys. And this includes the 2 pans, the 2 weight hangers, and the string, and the weights I'm adding on, such as the 10 grams, this is 1 10 grams, and this is 5 2 grams. So all that added together, and we measure very carefully to the nearest hundredth of a gram, I get 130.92 grams. So that's M1 plus M2, but not including the pulley masses. So we have to add 11 grams to that, so it'd be 130.92 plus 11, that's 141.92, or about 142 grams mass difference. Again, I'm talking grams here, times g gives you the weight. So our slope, in other words, I already know what the answer should be according to this and Newton's second law, about 142 grams mass difference. So let's load this thing up, and here's how we do the experiment. I'm going to add 50 grams to each side to kind of cut down on the percent air from the balance and so forth. So it should be just sitting here. If they're pretty close to 50 grams, they're really close to 50 grams because it isn't slowly accelerating, even though there's a little bit of friction there. Now I'm going to put 5 2 grams and 1 10 gram on this side. So that's an accelerating mass difference of 20 grams. Oops. Now the key to this experiment is we only want one independent variable, that's the force, the weight difference, and one dependent variable, that's the acceleration. That's what happens when I let go of this. So that means we have to keep the mass, the total mass, the same, which means we can't just take masses off and have this accelerate less because there's less mass. We have to take a mass off of here and put it onto here. So right now, this total mass here is roughly 20 grams more than the mass on the other side. So what you need to do, probably at every one of the 5 trials you're going to do, is to take these and take them off like so, put them on the pan, and measure that mass to the nearest hundredth of a gram, and measure the other mass to the nearest hundredth of a gram, because we're assuming that all these 2 grams are really 2.00 grams, and they're not any different. Well, they're just plastic things, so they might be somewhat different. So you need to check the mass of the heavier and the lighter mass, and that mass difference is the mass difference in M1 minus M2 times g, which is your net accelerating force. So let's go back and do the experiment then. Okay, well, we'll do one demonstration run. You'll be doing, I think, 3 or 4 runs, or 4 or 5 runs of each of 5 different weight differences, mass differences. So we go to Logger Pro and select Logger Pro. And again, we get our graph ready to go, just like graphical analysis. We go to the File menu, click on File, and open. And we can scroll down here on the menu and we have probes and sensors. This is a sensor. And if you click on that, you can go down to the Photogate option. Photogate. And if you scroll down here, you should see pulley. That means smart pulley. So that calibrates the system so that it knows that it's using a smart pulley, and every time the cord moves 1.5 millimeters, that's the next data point. So if you push the connect button, then it turns this rectangle up there green, which means we're ready to collect. And really, you don't have to do this, but since this is the distance versus time, we're not interested in that. We can get rid of that. And this is the acceleration versus time. We're not interested in that. We're interested in acceleration. We're interested in the velocity versus time graph. And if you want to, you can expand that graph to fill the screen by clicking on these little squares and dragging it up. Okay, so now we have a big velocity versus time graph. It even says velocity versus time. How convenient. So all we have to do is do the experiment, which means, let me load this back up. You don't want the strings swaying back and forth, because that actually affects the tension a little bit, and that's what we're not wanting to do. So that's the case. Cursor over to the collect button. That's my left hand, so it's not that handy. And then you don't have to worry about which comes first, the button push or letting go. I would push the button first and then let go. It can be pretty exciting with a 20-gram mass difference. So here's the mass falling, and here is it bouncing around and doing crazy things that you just saw it do. Fortunately, it stayed together, and so we've got it set so that it barely hits the little pad down there, and tends to kind of dampen out the motion. So what I need to do is hit the automatic scale button. That stretches it out, and I can stretch it out even further by changing the horizontal scale to 3 seconds instead of 4 seconds. And so that gives me, all this is just extra gravy, niceties. You don't need to do that. We're interested in the slope, which of course we get by pushing down and left clicking. That includes the data from down here all the way to up there. So from here to there, that looks like the best part, the nice and linear part of the graph. And so I'm going to take that, edit that out. It's called region of interest. And so you just click down and hold it until you get this double dense gray pattern covering the data you want to look at. And then you go to your, since it's supposed to be a linear regression, go to your linear fit scale, and it's going to calculate. So we have a slope of 1.251 meters per second squared, and an intercept that isn't 0 because there's friction, and the correlation coefficient's 1. Now that's pretty impressive because there's about 200-300 data points from here to here, all those little spokes going by as it falls down, and so you've got lots of data, but it still extremely carefully fits a straight line. Okay, so the slope And we can also double click on that box and hit the show uncertainty button, and you get the error in the slope, which is wonderful, because that includes all the errors in the experiment. And as I say at the end of the write-up, there's two ways to come up with the error, and that's take it off this wonderful final answer slope value, or you can estimate the errors, which we'll talk about later also. So the error is plus or minus 0.001, so it's 1.251 plus or minus 0.001. That's extremely accurate. Now, when you do this a second time, which I won't do, you may get a slightly different answer, because maybe you jiggle it a little bit when it started and you give a little speed that it didn't have originally, or something's wobbling or something up here, and you might get a little bit different answer there. So those are the data points you want to take. The next answer might be 1.255, the next one might be 1.248, but they're all very, very close to each other, kind of within that error limit of plus or minus 0.001, we hope. So that gives you a very accurate slope, which is the total mass of the system, which is what we're looking for. So it should be a pretty accurate experiment if all the assumptions we've made about the rotating wheels being not a big problem and so forth are true. So do this 3 or 4 times. I forget what I've mentioned in the lab write-up. Do it a few times, get an average, and that will also, if this comes out 1.251, the next time it comes out 1.248, and the third time it comes out 1.255, your error there is not this error, but it's bigger than that error, because it has to do with the way the equipment works, not just how well you fit the straight line. So that will give you your error in what we're looking for, the total mass of the system. And the slope is the total mass of the system. It's pretty nice. Okay, so that was the first run, and you want to do 3 or 4 of those to get an average. Use the maximum deviation as your error, not the number that's listed here as the best fit for that particular run. But the next run, when you're ready to do that, you take these off after you move one 2-gram mass, and again they're now all guaranteed to be 2 gram, from the right side to the left side. Okay, so what is the mass difference now? Well, there used to be 20 grams mass difference there. Now I've taken 2 and put it over here, so there's 18 grams there and 2 grams here. The mass difference is 16 grams, right? Okay, so we repeat the experiment with the 16-gram mass difference. You do need to take these off and mask them again individually, just because that's such an accurate instrument. We don't need to introduce any error in the masses, because we have a really quick and dirty method of getting a very accurate result for the masses. So this mass ought to be about 2 grams less. This mass ought to be about 2 grams more. You can kind of see that in your data, and then you simply repeat the experiment with a 4-gram smaller mass difference, and then another one, and another one, another one, until you once again regain this 10 grams here and 10 grams here. Nothing's going to go anywhere. Okay, so that's your second series of runs starting now. Thank you. That's it.